Hey guys, so here's an example of a complex ion or common ion equilibria. So in this case, we're going to be adding silver chloride to a solution of sodium cyanide, and the silver chloride should be more soluble than normal because the silver is going to complex with the cyanide to form silver dicyanide. Okay, so what do we do here? Well, let's start out with our equations. So we're going to have, let's pick green AG. I'm just going to make this a little bit bigger. There we go. AgCl, and it's going to dissociate into silver and chloride. And then we have our other equation where we're going to have silver ion and then you're going to have cyanide coming in. So we're going to have two cyanides, and these will be complexing with our silver cyanide. Cn2, and this is negatively charged overall, of course. Okay, so something I want to point out is that this AgCl right here is the only thing that is solid. Everything else is aqueous, but I'm not going to put the signs in because it's too hard to write that small. Okay, so now what? Well, we see that some species on our equation cancel. So we have silver canceling. So that means that our net reaction is going to be AgCl, or yeah, AgCl, okay. AgCl, silver chloride, plus two cyanides, is in equilibrium with our silver cyanide, which is also aqueous, which is important, and chloride. Okay, so now what do we do? Well, let's just assume that this first reaction goes to completion. Or, no, we don't. Okay, so let's make an ice table. Why not? Because we know the initial conditions. We know that initially the cyanide starts out at 0.2, and we want to find out how much the other species can increase to equal our KEQ value, which we'll calculate from the KSP and the KF. So right now, we're going to be forming our ice table. Zoom, 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 zoom. This is a messy ice table. Anyways, okay, so AgCl in here, remember this is solid, so we don't really care about it. Our cyanide starts out at 0.02 molar, and this subtracts 2x because there's two of them, and so total we get 0.02 minus 2x. Our AgCN, so we're going to assume that this starts out at 0, which it does, and then so does the chloride, and then we get x, 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 which means we get the equilibrium constant, which I'll call K equilibrium, equals, oh boy, so we're going to have silver cyanide 2 minus times chloride all over top of cyanide squared. Okay, so now let's relate these values to one another, because right now we can't, the values of chloride, cyanide, and silver cyanide, they don't really make a whole lot of sense. So how could we make more sense of them? Well, excuse me. Okay, so let's look back up here at our reaction. So we're starting with some cyanide. So it's pretty... I'm sorry, I can't even talk. So our cyanide starts at 0.2. So I'll write this in a different color. So cyanide starts at 0.02. And then some of it goes this way to form silver cyanide. So how much of it's going to form silver cyanide? Well, if we go 0.02 minus 2x, and x is going to be our constant for what's going over here. So when 2x cyanides go away, they're going to form 1x silver cyanide and 1x chloride. So this is our cyanide concentration, and then our chloride, that leaves chloride equals our silver cyanide, CN2, which is equal to x. Because now we can relate our x values to one another. So up here we have x times x over 0.02 minus 2x, and then this is all squared. Okay, and now what does this equal? So what is the KSP, or the KEQ rather? So in this case, the KEQ, because both of these reactions are, so we know this one's a KSP, we know this one is a KF, and they're both going to the right side, or they're both going the right direction to be KSP and KF. So we don't need to take the inverse of anything. We just go KEQ equals KSP times KF. Which equals our 1.8. Okay, I'm running out of room. So we have 1.8 times 10 to the negative 10. And we're going to multiply, even though it's written underneath, 5.6 times 10 to the power of 18. And once you multiply those through, we get that this equals 1.01 times 10 to the 9. Okay, so I'm going to move on to a new page, but the important things are this right here, our equilibrium equation, and our equilibrium constant. So I'm going to go ahead and rewrite this. Let's see if I can do that. Cool. So where were we at? We were at x times x, which I'm going to write as x squared now, over 0.02 minus 2x squared equals, and then we had 1.01 times 10 to the power of 9 for equilibrium constant. Okay, so how can we solve for x here? Well, you see everything here is squared on this side of the equation. So why don't we just take the square root of this side and the square root of this side? That seems pretty easy. And then we get x over 0.02 minus 2x. And now that is equal to 3.176 times 10 to the power of 4. Okay, and from here we can solve for x, which is going to be okay, so I'll skip a couple steps in the simplification, but basically you're going to get x equals 635.2 minus 6.352 times 10 to the power of 4. And because, and this is x, and because our 3.52 times 10 to the power of 4 is so much greater than x, we can basically say this is equal to 0, get rid of this x, and then divide this number here by, let's get rid of the negative sign, by 635.2 to get our x, which is our solubility, is 0.01 molar. Which seems about right, because we have the Kf value for our silver cyanide being very high, and we have the solubility being very low. So if we assume that all the silver chloride that dissociates is complex with silver cyanide, we get this exact same value. Basically half of the cyanide concentration because there's two cyanides. So it's pretty much exactly what we would expect. Okay, so hopefully that was fairly clear. I stuttered a couple times, but yeah. And I think I'll do one more example of common ions.